Right. I want to take this opportunity to welcome all of you once again to the valley of the shadows of quantitative analysis, specifically regarding regression diagnostics. Now, some of you, or all of you may be aware that we've already looked at regression. We've looked at simple regression, we've looked at multiple regression. The essence of what we are going to do today is when you do regression, sometimes you get a result, bad result. And the bad result is as a result of some certain things that must be in place, but you did not make them in place. You didn't put them in place, and as a result of that, your results is telling you that you should have checked those assumptions. You should have diagnosed to see where there is a problem and solve the problem. And based on the diagnosis, you can now have confidence, reliability in the work that you've done. And this is known as regression diagnostics. That's what we're going to do. So why do we do that? We need to verify that analysis met the assumptions of the classical linear regression model, the Gauss-Markov assumptions. And once they satisfy it, you're cool. One of the assumptions is that there must be linearity, normality, homoscedasticity, no autocorrelation, no multicollinearity, or no high multicollinearity. Sometimes it's known as exogeneity of the independent variables. There must be independence. Among the independent variable, there must also be independence among the errors. And there must also be independence between the errors and then the independent variables. And when these things are flouted, we have covariation, autocorrelation, and endogeneity respectively. So all of these are assumptions that we have to check. And that is the essence of our presence today. So let's recap of our Big Mac sales that we have. This is the data set we have been using all along. And in this data set, we estimated this OLS regression. These were the commands we used to estimate the OLS regression. And we got this. And we ended at this the last time. We even went ahead to interpret some of the variables as if they are great, when in reality, they're not great. There was one particular guy here who was really good and trying to interpret. I've forgotten his name. If he's around, he can just identify him for me. And we went to, on average, giving blah, 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 blah. Now, the question is that even though we're interpreting them, some of the variables were not significant. And how do we know? Well, we've already concluded the last time that significance is determined by checking the p-values. And any p-value that is more than 0.05, like the ones I'm underlining, they are not significant. It means that they are all above 5%. So the independent variables are not significant at all. So how do you deal with this? The moment you have a lot of insignificant independent variables, that is the first way to realize that you have some sickness in the data. Okay, so many insignificant variables. So why will you put a variable into a model when it's not significant? Okay, so that is the first thing. So we realize that there is a problem. The thing is that even if there is not, even if you think there is not, check it and confirm it. So the first thing we are going to check is known as multicollinearity. What is multicollinearity? Multicollinearity exists when two independent variables are so highly correlated that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. So two things are the same, like a husband and a wife are so close together that one supporting the other in a law court case is irrelevant because they will support each other anyway. So whatever one will say, the other will confirm. So having both of them in the box to testify is like redundancy. It's a repetition of the whole thing. And in life, there are certain things that may be multicollinear. For example, height and weight. Okay. They may be multicollinear. Height is determining something. Weight is also determining something. But the two of them themselves are correlated with each other. Because as your height is increasing, your weight is also increasing. As your weight is increasing, your height is increasing. They move together. Education and experience. Okay, both of them will increase salary. But then it's possible that it is your experience that leads to your more education, or having more education is likely to give you experience. A perfect multicollinearity is male and female, where it is a dummy. If you're not a male, you're a female. Okay. So when you have situations like this, and this last point I made is important because it helps you to understand why you should not consider multicollinearity among dummy variables. All right. So when there is multicollinearity among the regressors, the predictors, the independent variables, what do you do? Well, first of all, let's look at how it will affect the entire result. The first problem is that the standard errors will be disturbed. They will be increased. They'll be biased. And tell you what, if you check this result here, the coefficient column, okay, the coefficient column here divided by the standard error will give you the t statistic. And it is when you read the t statistic from the table, that is what gives you the p-value. So if you do this and you realize that this standard error is too big, it means that when you divide this one by the standard error, the t statistic, which is supposed to be big, will be too small. Okay. I mean, just as an example, look at the t statistic here. It is 78. No wonder the p-value is 0. Okay. So when the t statistics are quite small, like this one here is very small, then the p-value is likely to be large. Okay. And that is because the standard errors are bigger. So when you check, when the standard errors is too big, the t statistic becomes too small, and then the p-value becomes too large. And this is where, so when you have a situation of multicollinearity, then you are going to cause the standard errors to be very, very, big. And when that happens, this t statistic, which is defined as the beta cap minus the true beta divided by the standard error. The standard error is the square root of the variance down here. Okay. This one is disturbed. Now, multicollinearity will not affect your prediction, and you can see that we can predict. However, it will affect the p-values, basically. So how will you know is there? How will you know that you have a problem already of multicollinearity? Well, one of the things you got to do is to use scatter plot and correlation matrix and variance inflation factor. 3 things: a scatter plot of the data, a correlation matrix, and then variance inflation factor, especially the variance inflation factor. You see, the variance inflation factor tells you how that particular independent variable, how its variance is inflated. And you see the word inflation is something normally we don't even want. So how is that particular independent variable, its variance is inflated? And if you want to measure the variance inflation factor, it's basically taking the R square you already have. Okay. So you take the R square, okay. And when I say R square, I'm not talking about the R square of all of them. No, I'm talking about the R square. Suppose you had to run a simple regression. So if you run a simple regression between a dependent variable and one of the independent variable, the R square that will come out, what we sometimes call a multiple R. that R squared that will come out. That one. You do 1 divided by 1 minus that, and that will give you the VIF. And the reciprocal of that VIF is also called the tolerance level. The tolerance level is simply how much you are willing to tolerate the variance inflation. What is the criteria? How do we use this VIF? Suppose you've calculated it, then what? Well, then you check whether it is 1. If it is 1, it means that that particular independent variable has no correlation with any of the other independent variables. That's what it means. It has no correlation with it. It means that that variable is cool. You should keep it. However, if you get a VIF bigger than 5, it suggests that there is a modicum of multicollinearity. There is some element of multicollinearity. The moment it is more than 10, hallelujah, then there is a considerable multicollinearity caused by that particular predictor, that particular regressor. So in this case, what do? You remove it from the model to see whether its removal can cause anything. Whether it will dwindle the R square or not. You check it. But look, if you are doing a research, for example, and that variable is important, let's say that education is important in affecting salary, and it is part of your literature review, and you want to remove it, then you got to think twice. So sometimes you have to check certain things before. Okay, so how do you cure it? I've already told you, remove the independent variable with the largest VIF, and you should do that one at a time, and then you rebuild the model. One at a time, then you build a model. Sometimes you don't have to remove it, but you combine it with another variable, another independent variable, so that you are able to tell the story that you want to tell. Now, if the correlation, some of the correlations are close to 1, okay, or close to -1, then it again means that that variable is likely to have a multicollinearity issue. So we're going to show how we did this in Python. Our data, if you can remember, our results we had from last time. And by the way, you have this, and I know you've typed it, you've copied it already. Okay. So what we are going to do is that we had this final work known as train features. That is the scale data. Okay. And this was a result of our analysis that we had, the OLS result. We are going to check whether this very thing has got multicollinearity. So we run this VIF series on this train feature. Okay. We run the variance inflation factor on them, and then we look at the results. And I'm going to show you this here. Yeah. Like I said, you can do it yourself. Okay. Okay. So that is it. This is a result. You can see I just ran it here. And then those of you who are co-hosts, can you mute the one talking? Can you mute him for me? Those of you who are co-hosts. Those of you who are co-hosts, can you mute the one talking? All right, okay. If it happens, it means I need to mute everybody. All right. So this is it. Okay. So now we've been able to check. You can see that forget about the constant. The constant is not key. What is key now are the others. And you can see that straight away, outlet age has got a very high multicollinearity. It's more than 10. Okay. The rest are below, but then there's also one here, outlet size. And then that is outlet size, whether it's medium or small, they are all big. Location type is also quite big. Outlet supermarkets is also there. and some few other ones are there. So we're going to do it iteratively, one by one, to see what the situation is like. So outlet age has a high VIF. So we're going to drop that from the model. We remove that from the model, and then we rebuild the model again. So how do you remove that? Well, we use this command here. So I write my train features. It was first of all called train feature scale, but now I want to add the word new to it. Okay. Simply because I am creating a new kind of model. And then I drop outlet age from that model. So now I'll move from my OLS model 1, and I'm going to, now that I've removed outlet age, I'm going to rebuild model 1 to model 2. Okay. I will do this same OLS model, this time on the new. So you can see that it's train target, and then the independent variables. The dependent variable is still train target, but independent variables is no longer train features scaled. It's rather train features new. That's what you do. You run that model, you fit the model, and then you print the results. Okay. Now let me show you the result before we look at the comment. So look at this beautiful outcome. Okay. So this is our results here. And in this result, remember we're looking at what's the name? We're looking at outlet age. Okay. Now, as you can see, we remove that. Okay. Outlet age, we have removed it. So if you check these ones, it's no longer here at all. Okay. Now that outlet age is gone. See what is happening. Okay, look at the p-values now. The p-values, some of them are high. In fact, some of them are now very high. Okay. The R-square hasn't changed. So they are very higher, than we can even imagine now, which means outlet age was really, really, a challenge. But what it means is that something else is causing a lot of problems. So now that you can see clearly that the p-values are big for some of these, we will now check the VIF again. Okay. But before we check the VIF, note something. All the dummy variables, everything that is a dummy variables, and again, I've asked you this in your assignment. All the dummy variables are variables that you don't have to check their multicollinearity, because obviously they are going to be multicollinear because they all come from a similar thing. So if it is item type, they are all item type. So it's not a good practice to consider the VIF values for dummy variables because they are correlated with the other dummies or the other categories anyway, and therefore they will have a high VIF. So the next thing we are going to do is to remove all of these very ones that have a higher p-value. So that's what we're going to do. So if you look at the item weight after we removed the first one, you can look at the item weight, you can see that the p-value is very big, 96. The p-value. So that's almost 97% bad. So what it means is that the next thing after removing the dummies, we are also going to remove the item weight. So let's drop item weight. So watch this now. We are going to build a new model, but we called it what? Train new feature scaled, new drop. And now we drop all of the item type, okay? Not one, all of the item types are many. You can see that item type were many. Just so you can appreciate it. Item type, we had this one, Thai bread, breakfast, canned, dairy, frozen, hard drinks. All of these we are going to drop. Anything called item type, we're going to drop them. Okay. And then, of course, we will also drop item weight. So let's drop them. You see, dropping them requires that you run a command for that. So you can see that I'm dropping the item type here. I check the VIF of them now and check the VIF. Okay. After that, you can see that the item weight, the VIF for it has gone down. Look at the item weight on the right here is 1 over. Again, when you go to the command. So after this, I drop them here. So you can see that this is a dropping of them. And then you check the VIF. And this time, look at the item weight. Item weight VIF has reduced. Okay. Now, if you can remember the VIF for item weight before, okay, it was like that. But the reason why it was like that was because of the size, okay, outlet size. But now the item weight, the VIF has come down. Okay. And so now that it's come down, let's rebuild the model and see whether it's significant. Now we go and check the model and look at it. Item weight. Item weight is still insignificant. Okay. So item weight, the VIF has reduced. We rebuild the model. Okay. It produces another insignificant p-value. So what do? In our next model, we'll remove that. This time we call it new 3. Okay. In our OLS model 4, we rebuild that. And when you do that, you will see it here. So in this next one, you see that I've removed the item weight. So after removing it, now there's no item weight, okay? But then look at outlet size. When you check the VIF, outlet size, whether it's medium or small, they are quite big, okay? So once again, we will remove outlet size. And not only outlet size, outlet location types 2 and 3 are also having high p-values. And look at that here. Okay. So this is outlet size. The p-value is 58 and 56. Outlet location type 3, it is 78. Type 2 is 15. Okay. So the p-values are giving them up. So what we are going to do is that we're going to remove them all. And again, using the same approach, just give them a new name. Using the same approach, remove them and then rebuild the model. Okay. Now, let's look at after removing them and rebuilding the model. Check the VIF. The VIF, most of them are getting what? Below, okay, which is good, but that will mean that we need to check the p-values then. So we rerun the model again and check the p-value. You can see that outlet size, small and big, are still having a p-value of that. So remove them, check the VIF, and run the model one more time. And now, after running, it's just a process repeatedly. You now see that item visibility is having a p-value, which is 25%. Item visibility is not looking good. So we go back here. We run the OLS model, and then we drop item visibility. And this keeps on going and going, check. So the key point is this. You check the p-value and check the VIF. After doing the VIF, it's high or low, it's good. Now check the p-value. The p-value gives it up. You remove that. You move to the next one. No. You keep doing that until you get to the final model. And ladies and gentlemen, let's look at the final model. Okay. So I did that, checked that, checked that, and now this is our final model here, which is model 7. Okay. Now look at model 7 very carefully. If you check model 7, everything seems to be cool, except that it appears that item fat content regular is slightly almost insignificant at 5%. Okay. It's slightly almost insignificant. But you can see clearly that item fat content, again, I've brought it here. It's insignificant at 1%, but it's not insignificant at 5%. It's significant at 5% because it's more than 5%. It's 4.7% when you look at it here. So this final model is a great one to look at. It is a great one to look at. And again, that's the same thing that you can see here. Now, at this stage, you can see that all the VIF, okay, and you can see that here. Check the VIF, and I did that here. Check the VIF for all of them. All the VIF are less than 5, which is good. Okay. They are all less than 5, which is good. And if you check the p-values too, they are all looking good. So our conclusion is that all the VIFs are now less than 5. So no multicollinearity is present. All the p-values are also less than 5. Okay. So it means that they are all significant. Now, there's something you want to check here, and this is very interesting. Even after removing all of these values, I want you to look at the R square. Look at the R square. The R square is still what it is. It was 56. It's still 56. So it means that those values, those variables were in the model and they were doing nothing. Because normally when you remove them, the R square should come down, the adjusted should come down, it's not. Which means that they were irrelevant. They were not playing any significant role in the model. So the R removal sort of makes sense. Okay, so that is one key thing. But let me just put on a record here that if you do this dropping, it means that you're going to lose some information. Because as you keep dropping, okay, let's say that you needed a particular item weight and now you dropped it. It means that you're going to lose some information. So this regression approach might not be the best after all, because you're going to lose the information. So one thing you can do is you can use principal component analysis. And we shall do this next time, which will help you. It's easier though. It's very simple. It will help you to cut down the high multicollinearity in the data by combining some of the variables, those that are correlated. That's one way. If you don't want to remove the variable, you can use ridge regression, lasso regression, elastic net regression. All of them can handle the situation. So that is how you deal with multicollinearity. At this stage, you should know that multicollinearity exists when two separate independent variables are highly correlated. All independent variables are highly correlated. And the only way we check whether they are highly correlated is looking at their VIF, their variance inflation factor, and rerunning the model to check the p-values. That is how you deal with it. If you want to keep the variables, then you run ridge or lasso regression. So in our model here, we will be finally left with what you see here. This is our final model. Okay. Our independent variables were many. We remove most of them. Now we have item MRP, item fat content regular, and then the outlet supermarket. This is our model that we have. These are the only relevant things that are happening in the model. Let's look at the other assumption that we got to meet. The next assumption in regression is the error term. We said the expected value of the error term must be 0, which means the mean of the residual. The error is the same as the residual. The mean, not the individual residuals, but the mean of them should be 0. Let's quickly check whether that is so. Okay. Our model is this. Our final model is model OLS 7. And now we want to check the residuals here. Okay. We set that thing to find the residuals of the model. And now we find the mean of the residuals. So we run to find the mean of the residuals. And we get 1.580778060, blah, 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 E minus 12. This E minus 12 is an important number. Okay, it means that there are 12 zeros before the first number, which is 1, 5. There are 12 zeros before. And then after the first zero, you put a dot. So it becomes 0.11015, blah, blah, blah. And this is approximately 0, which means that the expected value of the errors are 0. Okay, you know what this means? It's beautiful, because what this means is that the assumption has been satisfied. The axiom that says that we should have 0 mean errors has been met. We are good to go. And these things, if you're doing a real research, is talk about it. The next one is the normality of the residuals. Okay. We said the last time that the errors or the residuals are independently and identically distributed. Independently and identically normally distributed. Let's be clear with that. With a 0 mean and a constant variance. The word is normally distributed. What does that mean? It means they are normally distributed. It's like a bell shape. They should be like a bell shape. That's what it means. Please note that certain things in life are not normally distributed. A Poisson count. For example, the number of people who queue in front of a desk per hour. We've done Poisson distribution, binomial distribution, exponential, all of these things. The number of traffic crashes per intersection per year. All of these things are not normally distributed. So let's check whether the residuals are normally distributed. You can use graph and you can use test statistics. Quantile normal probability plot is one graph. The probability plot, BP plot, and KQ plot. You can use kernel density plot. You can use histogram. And then after that, support it with a test statistic, the Shapiro work. Now, let's look at them right here and see whether they make any sense. So I'm going to use this command called sn.histoplot to check whether the residuals are normally distributed. Okay, so let's do that here. So I do this, I run it, and there you go. Okay, you can see that the residuals are normally distributed generally, graphically. Can see that they appear to be normally distributed. They are all centered. Look at the peak, centered around a 0 mean, as we want. Question is that true? Let's get a test to prove that. So to do that, we import from SciPy, okay, the stat command. We run the Shapiro test. And let me tell you a little bit about a Shapiro test so that you can appreciate it well. And these are questions that you get, most of these things, so that's why it's important to you. Now, the Shapiro test is a test for normality. It has a null hypothesis. Every test has a normal hypothesis and an alternative hypothesis. You should know these things. And then after that, you have a test statistic. Normally, you check the test statistic against a critical value. And once you do that, you also check the p-value against alpha. The default alpha is always 5%. Okay. Now, what does a null hypothesis say? The null hypothesis says that the data is not normally distributed. Okay. And whenever the p-value, please take note. By the way, this is a test statistic, W, the W for the Welk. Okay. When the p-value is bigger than 5%, then you reject the null hypothesis. Take note. It's the opposite of how you know all of hypotheses. So when the p-value is bigger than 5%, then the data is rather normal. And the p-value is bigger than 5%. So when you check our own here, look at it here. This is the p-value we had. The p-value is 97%, which means it's bigger than 5%. And that means that our residual is normally distributed. Okay. So that's a clue. Whenever the Debye-Waston test, the Shapiro work test is close to 1 for the samples, then it means that the data is normally distributed. When the the p-value is close to 1. So that is how you estimate it. And in this case, so all you got to say is that our assumption of zero mean is satisfied, and the data is also normally distributed. So that is how you check for normality. The next one is to check for linearity. Now, what is linearity? Well, an example of linearity is what I've shown here. This is a linear model. Everything, the independent variables are linearly correlated, linear in parameters. So if you increase the independent variable by anything, any unit, the dependent variable will increase or will reduce by the value. It's not going to increase and reduce at the same time. It is or, it's not and. Because if it increases and reduces, then it's no longer linear, but it's rather quadratic. Now, suppose you have a linear model like this, what you see here. And this linear model you have here, it is linear. Sorry, the model itself wasn't linear. The model was this, nonlinear. Now, when I say nonlinear, it's fractional here. Fractional here is not linear, it's nonlinear. But then, even though this thing is fractional, you rather fit a linear model on a fractional situation, on a nonlinear model. So the thing is not linear, but you force linearity by using OLS to fit the linear on the nonlinear. You have caused a big problem, caused a huge problem. The reason why you're going to have a problem is that the residuals that will come out, and how do you measure the residuals? The residuals is actually the expected minus the actual, or the predicted minus the actual, or the fitted minus the actual. So what the residuals, which is the what do you call it? The true value, okay, minus the predicted value, okay, the actual minus the predicted value. This is the actual. What I've circled here is the actual. When you take the actual minus the predicted, because this is what you did, okay, this is the one that you actually estimated. So this becomes a predicted or the fitted value. The errors are going to be having these errors. And these errors, when you look at them carefully, the fact that this one is not linear, is fractional, meaning that the entire residual is going to be nonlinear. So here you have a nonlinear residual plot, which will not be a line, because a plot is supposed to be a line. But now the residual plot becomes a curve, all because you have a wrong model. Now, when this situation happens, then you have not satisfied the linearity assumption. How do you detect whether you have a linearity issue or you don't have an issue? If your residuals are linear, that's cool. If they are non-linear, that's bad. But one way you can check is use residual plot. You plot the fitted value and then check whether the residuals don't form a strong pattern. That word is very important. They do not make a pattern. What is a pattern? I'll show you very soon, but check this. Guys, tell me. And you can raise your hand and tell me, or you can just tell me into the mic. This is a graph, a line that I'm coming to show, or something that I'm going to. Does this show a pattern? What I just drawn, does it show a pattern? You can tell me. Theophilus.
So as y increases, x decreases.
You didn't answer my question. Does this show a pattern? Yes. No.
Yes.
Yes, it does. This one that I've shown here, the second one, does it show a pattern?
No, please.
It does. This one that I've shown here, Does it show a pattern?
No, please.
No.
Yes.
No, please. No.
Somebody says yes. Wow. Come on, guys. Now, this one that I'm showing here, does it show a pattern?
Yes, please.
Yes,
Yes.
please.
So you should know what we mean by something shows a pattern or it doesn't show a pattern. Okay. That's basically what we mean. I just wanted you to understand that. So what we are saying is that the residual should be random. It should be uniformly scattered on the x-axis. It shouldn't show a pattern. That's it. It shouldn't. Because if it does, so we are going to check our residuals. We are going to plot it. We are going to fit the OLS7. Okay. We're going to use SN the residual plot, but we're going to plot on the x-axis the predicted. That's a fitted. And then the residuals on the y-axis. And then we'll plot the residual plot to see how it looks like. So this is done there when you check your slides there. I did that here. And this is it. This is a residual plot. So now my question to you is, when you look at this residual, does it show a pattern? Does it show a pattern? What you see on your screen? Is somebody scared about what he or she will say?
No.
Does this show a pattern? Yep. No. Does it show a pattern? Some of you are typing. Now you don't want to talk again because you are guessing. Okay. All right. So there is some pattern here. Okay. There is some pattern, clear pattern. First of all, you can see that the way the thing is going, you can follow this line at the bottom section. It shows that something at the bottom here is coming down. Okay. Then something on the top there is also coming down. Then it rose and then came down again. Okay. It must have been centered around the zero line, but it's not. The errors are not randomly distributed. There is a pattern. And when there is a pattern, there is non-linearity. We have a problem of non-linearity here. Okay. How do you fix it? One way to fix it is to make the dependent variable log. Take the logarithm, the natural log of the dependent variable, and then rebuild the whole model again. When I say rebuild the whole model again, it's nothing. It's just a click one thing and everything gives you a different result. So let's take a log transformation of the dependent variable. So I come here. The dependent variable is called train target. So this dependent variable, I'm going to take a log of it. Okay. I'm not going to just take train target. I'm going to take, okay, after applying the numpy, okay, I take the log of the train target and I call it train target. And then I rename the model 7, I rename it, okay, but this time the dependent variable is what? Train target log, what I did here. But the independent variable is what it is always what it is here. And now I fit this new model. I still call it OLS, model 7, result 7. I fit this new model. And then we check the result. Okay. After checking it, remember that the result we are checking is not the other results. The result we are interested in is we come and check the residuals again, the residual plot. That's all we're checking to see whether this time it shows a pattern still or it doesn't show a pattern still. So this is what I've done here. And all that I went through, this is it. So look at this thing, what you see here. Does it show a pattern?
Sir, please, it doesn't.
Good. So you can see clearly that it doesn't show any pattern. It's all many. Okay. It doesn't show any particular pattern at all after the transformation. Okay. I could have written the mathematics of what I said, but again, I don't want to do that. But That's the key point. So there's no pattern in the residuals, and therefore we have been able to clear the non-linearity issue. Linearity assumption is now satisfied. So you got to go through these diagnostics to be sure that everything is in order. Now let's look at the summary of the model. Okay, and now that we have fit, if we want to see the result, now look at the result. Look at the R squared. Okay, and by the way, if you want to get a summary of the result, it's just a matter of just printing the summary of the result. And look at the R squared. It was 56. Okay, now the R squared has gone to 72. So just by taking the log transformation, in fact, this log transformation, it doesn't only solve issues about it does the issue regarding what do you call it? Regarding this non-linearity, it solves several other issues. Other issues you are solving by solving this problem. Okay. So the R square has changed, which is good. Now look at the results here. Okay. The results are still great, okay, but you can see that the item fat content regular has become insignificant. It's become insignificant. Okay. So that's something that you deal with later. But at least you've been able to take the log linearization of the model. The key point is the performance of the model has improved. Now let's go to the next assumption, that this is the last but one assumption. The assumption is known as heteroskedasticity. Heteroskedasticity. Now, if you pronounce it like that, it becomes easier. But if you pronounce it in a different way, it's not easy. Heteroskedasticity. The word hetero means different. The word skedasticity means the spread, the variance. This word is the longest word in econometrics. 18-letter words. What do we mean? I've explained it the last time. It happens when the variance of the error, that is dispersion from the center, how the error disperses from the center. Remember, the mean is supposed to be 0, and you just saw that graphically. Now, the dispersion from that mean should be constant. But again, what does that mean? The error variance should be constant, meaning that the variance of the error should vary across observation. Now, when there is a problem of omitted variables, when there are some variables you should have included, but you did not include, when there is a wrong misspecification of the model, or when there's a wrong specification of the model, which is a misspecification of the model, which is what you just saw when the model was supposed to be nonlinear, but you use linear. All of this will bring about heteroskedasticity. When there are outliers in the model, it can bring about heteroskedasticity. What it means is that the residuals are going to create an arrow shape or any other non-symmetrical shape. The residuals are supposed to not show that non-symmetrical shape. They are supposed to show symmetrical. By the way, when I say symmetrical, I'm talking about normal distributed shape. But when they don't show that normal distributed shape, then you have this issue of heteroskedasticity. So quickly, by this, you should know that if you want to even check graphically heteroskedasticity, you got to use the residuals. Let's try to understand this thing better, okay? Then you can appreciate heteroskedasticity more. Now, we know that homoscedasticity is when the variance of the error is constant. Heteroscedasticity is when the variance of the error is not constant. So you can see that not equal to, then you have equal to for the homo. Homo is like something like, looks like the same. The same. Now, when there is heteroscedasticity, the estimators, which later becomes a coefficient, they are still linear. They will not be affected. Linearity will not be affected. They are consistent, they are unbiased. The R square is still not affected, but they are no longer best. They are no longer efficient. In other words, the variance, which is supposed to be small, is no longer small. So the R square is still valid, but the p-values are not significant. That's what it means. And when there is, see, watch the word though, because sometimes some of these things, they are very easy to understand. The variance is supposed to be minimum, but it's no longer minimum. So it means that the variance is inflated, more or less. And therefore, it is not best, it's not linear. Well, it's best, it's linear, but and it's unbiased. Sorry, it's not best. It's not best. It's linear, it's unbiased, but it's not best. And therefore, it's not blue. Because blue, B is best, which means minimum variance. U is unbiased. L is linear. And because it's not B, B alone is not there. You can't say Lu. And so it's no blue. And when that happens, the standard errors, not a coefficient, the coefficient sum, but the standard errors are overestimated. I told you because the standard errors are coming from the variance. So what this means is that when you have a problem of heteroscedasticity, because the T statistics are affected, because the T statistics depend on the standard errors, the T statistics are affected, the p-values will be affected. Okay? The F statistics may be affected. The LM and the wall test are anything called test are going to be affected. And these tests will also affect the confidence intervals because the confidence intervals are biased. Because the confidence interval depends on the test statistic and then the p-value. That is not good. That's not good at all. Let's look at an example situation. Practically, what we mean by heteroscedasticity. Suppose that you model the household consumption. You model the consumption based on the income. And we know that the more income, the more consumption, generally. If you do this model, you are going to realize that the variance in the consumption increases as the income is increasing. If you realize that, see, watch it. First of all, we know that as income increases, consumption is increasing. But if the variance, the variability in the consumption, okay, is increasing as the income increases, then you have a heteroscedasticity issue. The last time I was giving you another example of this regarding whether you are living in East Legon and somebody else is living in Cantonment. And because those in East Legon have increased their income and therefore they are buying more, you have concluded that those in Cantonment will also buy more because they've increased. So how do you check whether there is heteroscedasticity? Well, once again, the residual plot, the error plot that we had before will give us a clue. But you also have to use a test. There are several tests, several. One of them is White test, Goldfeld and Kwan test, Bridge-Pagan test, Bridge-Pagan and Godfrey test, Coenca-Bassett test, several tests. Sometimes you just need about two of them, one to corroborate the other, and that's it. You don't need all. Okay. Now, what is a null hypothesis? Remember, every test requires a null and alternative hypothesis. The null hypothesis is saying that the residuals okay, are homoscedastic. We just represent delta with the residuals. The residuals are homoscedastic. That is, the differences between the residuals are zero. There is no difference in the residuals between one residual and the other residual. But then the alternative is saying that if only one of them differs from the other, then it means that at least one of the independent variable affects the variance of the errors. So that would nullify the null hypothesis. This second one simply means heteroscedasticity. The first one means that the residuals are homoscedastic. The second means that the residuals are heteroscedastic. You use an LM test, and the LM test is the sample size multiplied by the R square. If you check this test statistic and it's greater than the chi-square distributed critical value, then you're going to conclude that a significant evidence of heteroscedasticity occurs or is there. Okay. If the p-value is less than 5%, okay, and this is very important, then heteroscedasticity exists. Again, if you check it very carefully, okay, you will see that it is like the opposite of what you normally want. Okay, so you rather reject the null hypothesis if the p-value, you are rejecting the null hypothesis of homoscedasticity if the p-value is less. If we have a smaller error, then it means that there is heteroscedasticity. So if you want homoscedasticity, the p-value must be big, basically. So let's try this in Python. Okay. The test I used was the Goffard and Kwan test. That's what I used here. I tried that on this and I ran my model. Again, you can do this thing. That's why I'm giving it to you here. You can do this thing yourself. And let's look at the p-value here. But I can show you this here and look at the p-value. Look at it right here. The F statistic is 0.9395. The p-value is 98%. We said that if the p-value shows any number less than 5%, then it means that heteroscedasticity is present. There's nothing that shows here that is less than 5%. It's rather more than 5%. It's 98%, which means that we cannot reject the null hypothesis of no homoscedasticity. Okay? We rather say that the residuals are homoscedastic. And truly, the residuals are homoscedastic. And you can check that. So that is one way you can determine that. So once you say that, oh, you now conclude that the results clearly shows that there is no problem of heteroscedasticity. So we can rely on the earlier result we have for regression. And that is good. That is a very good way to analyze your work. Now, of course, you know what this means, eh? This doesn't mean that because you have solved this issue about heteroscedasticity, it means the other ones are also solved. That's why we go through each one of them one by one. And that leaves us with the last one. But before that, let's look at this. What if there is heteroscedasticity? Because in our case, there is no hetero. What if there is heteroscedasticity? Well, once again, using the, now please note something here, and I wanted to show you something. If you check what I ran here, I did not run it on my model 7. That was the log transformed with, sorry, I did. Okay. I ran it on the model 7, but I ran it on the train feature scaled new 6. Okay. If you check, I still had my train target, the log transform model. But then I used the train features scaled new 6. I just want to put that on record so that you know. Okay. If there is heteroscedasticity, and in this case there wasn't, but if there is heteroscedasticity, you can take the square root You can take the square root. Okay. You see that you can take the log of the y. We took that. That's what we use, but then it's still, it's still, well, that's why it was solved. But suppose it wasn't. Suppose we had used the old one. So you can see that the one that we used to solve the linearity was take the log of the dependent variable. And that log of the dependent variable is what has solved this heteroscedasticity, which shows that there's no heteroscedasticity. Okay. If the log doesn't work, you can use weighted least squares or generalized least squares, okay, or feasible generalized least squares. These are ways you can use to solve the problem. Just know that these are ways to solve the problem of heteroscedasticity. Good. Our last assumption for today. If you have a question on this last assumption, I've put it last because sometimes it can be tricky. So I'll slow down, but please remember to ask a question. If you have a question, then that will be fine. It is called autocorrelation of the errors. There should be no autocorrelation of the errors. This is it. This is it. What is that? Now, normally, we assume that the errors don't depend on each other. We call it independence of the errors. What do I mean by errors? I'm talking about error I and error J. What do I mean by error I and error J? Suppose you have some individuals, and then you have the salaries, and then the salaries, you have the salaries dependent on education and then on experience. And you have individual Kofi here. You have Amma there. You have Abba here. 3 people. And these are the salaries in thousands. So this person is collecting 16,000. This is collecting 14,000, and this is collecting 10,000. The experience of this person is 21 years. The experience of this person is 20 years, and the experience of this person is 5 years. The educational level of this person is, let's say, master's. Okay, this one is PhD, and this one is undergraduate. Now, this person will create an error. Kofi will create an error. Let's call it error K for Kofi. Amma will create an error. Let's call it error A for Amma. Abba will create an error. Let's call it error B for Abba. What we indicating here is that the error K should not depend on the error A. In other words, something that is influencing the salary of Kofi behind the scenes, that same something should not influence the salary of Amma behind the scenes. That's the whole point. This autocorrelation is about the errors, but you can see that in a cross-sectional model, like I'm doing here, what we are looking at is cross-sectional. So we are not brought time into it. This is not a panel data we are looking at yet. This is a cross-sectional data where we don't have multiple time periods, just at a time. The 2 errors must not be related to each other. That's why we have here the covariation between the errors must be 0. The errors, the disturbances relating to any observation, that disturbance should not be influenced by the disturbance relating to any other observation. So you can see these are the observations. And the disturbance relating to Kofi's observation should not be influenced or be affected by the disturbance related to Amma. When you violate this, then we have autocorrelation of the residuals. The word autocorrelation, correlation we know. Autocorrelation means that these are happening to this, what is happening to this is happening to that. And this is an example in a cross section. The effect of an increase of a person's family income. Okay, the effect of your income on your consumption expenditure. This effect is not expected to affect the consumption expenditure of another family. So you won a lottery, and after winning the lottery, your income has gone up, and as a result of that, you have bought a BMW. That your lottery you won should not make another guy also go and buy, another family go and buy a BMW because you won that. So whatever has affected his income, if it is coming from you, your winning of the lottery, that is where the problem is. That is a first situation of cross-sectional autocorrelation. What about if it is time? In time series, what we are saying is that whatever happened last year should not affect what you will do this year. So suppose there is a disruption in a company because of labor strike. Okay. Then this labor strike happened last year or last month. And this has affected productivity, output in one particular month. This should not be carried over to the next month. If it happened last year, the moment it is taken over, that same thing which happened last year is affecting the productivity again this year, then we have a problem of autocorrelation. So this is autocorrelation based on time. And it is the one based on time that is a big deal, not the one across individuals, but the one across time. So that is a practical example of autoco here. How do you deal with the issue? Well, let's look at this scenario. The moment you sincerely detect a pattern, okay, among the errors, then we have autocorrelation. So look at this graph here. Is there a pattern here? Is there a pattern?
Yes.
Is there a pattern or there's no pattern? Who can tell us?
Yes, please.
There's a pattern. What kind of pattern is this?
It's a cyclical pattern.
You saw it or you are saying it? I know that if I had hidden the word cyclical, you probably not remembered cyclical. So I hope that you said it from your head, but not because you saw it. Okay. So once there's this pattern of cyclicality, then you have autocorrelation here. Now, this second one, there is a pattern, an upward pattern. And this is, they are all moving in the same thing, but it's over time. Look at the whole thing. Okay. It's happening over time between you and UCAP. And so this is another one. Then there is another discernible pattern. Both you and UCAP are facing something over time. And this is both linear and quadratic trend that you can see. They're both rising and falling. This next one, there is no discernible pattern. You know, they are all kind of centered around the mean, the zero, over time. So you can't say that they are both rising and falling at the same time. No, there's no systematic pattern. And in this case, there's no autocorrelation. And then finally, there's a downward trend here. So there's a discernible pattern among the errors. Remember the last time I said I can use epsilon for the errors. I can use, U also for the errors. So these are examples of autocorrelation. Let's look at the nature of it. This is how you write the autocorrelation, and it's said to be known as the first autoregressive scheme or first order autocorrelation. The first order autocorrelation, I've given you two of them here. The first one is a cross-sectional. If you check it very carefully, the cross-sectional one, okay, there is no time. There is only individuals with I. And there is a connection between I and J. Okay, so this I, its error is VI. But then there's a relationship between this error I and this error J. And that relationship that you see is this gamma. So this gamma symbol here is telling you by how much there is an influence between the error I and the error J. The errors are being, one error is influencing the other, and we don't want that. The second one is the actual autocorrelation. That's the one we talk about a lot when we talk about autocorrelation. Okay, it is the error of today, and of course, we know that it will be affected by an error of today, but it's also being affected by the error of yesterday. The error of the yesterday is the t-1. By how much it is affecting the error of today is a rho. Okay, the Greek letter RHO, rho. So there is autocorrelation between the errors of yesterday and the errors of today. Now, what is the rho? Well, first of all, the rho is between -1 and +1. It is a coefficient of autocorrelation. And like I said before, the VT is basically the usual random noise. The rho will tell you the level of the correlation between the error of the past and the error of the present. Now, if we take the variance, because there's autocorrelation here, don't forget. And we have demonstrated autocorrelation here. And it is called AR1. If the variance of the current error is still homostochastic, and it is, but then it is correlated. It's correlated with yesterday's error, and probably is even correlated with the errors of before yesterday's error. You see, the strike issue might continue year after year or month after month. There are some people who have supported some political parties since they were born, and this error has continued and continued and continued several periods of time. So you can have homoscedasticity, and that doesn't mean that you should not have autocorrelation. You can still have good and then a bad thing inside one thing. So you still have serial correlation, which is another name for the autocorrelation. All right. So what does it mean if the rho is 0? Now watch it carefully here. If the rho is 0, and look at it mathematically up, if the rho is 0, it means you have multiplied the 0 by the epsilon t-1. So the whole of this is 0. So this error is just equal to its error, its current error. Okay, so epsilon is equal to VT. Epsilon t is equal to VT. That's it. And that means that there is no autocorrelation. The residuals are not autocorrelated if the rho is 0. But rho can be positive and rho can be negative. And whether your rho is positive or negative, there is autocorrelation. It means the residuals of yesterday and the residuals of today, or the residuals of one observation and the residual of the other observation, they are autocorrelated. If the rho is non-zero, if the rho is not 0. Now, what happens if the residuals are positively autocorrelated? Well, one, these are the problems. The variances are underestimated. The values of the F statistic and the T statistic are also overestimated. Now watch the words. the variances are inflated, bigger. And whenever you have a bigger variance, that means it's sort of the standard errors are big. You remember the coefficient divided by the standard error is a t-statistic. And now when the bottom, the denominator increases, the whole ratio will fall. So the t-statistics will come down. That's why, we have a bad t-statistic. So it's not good. The p-values will be affected as well. How do you check whether there is that problem? Well, again, use the residual plot, because this is all about the residuals. So plot the residuals. Plot the residuals. If the residuals are independent, then the residual plot should look randomly scattered around the mean, around 0. But if we see a clear pattern, cyclical pattern, then there is autocorrelation. So let's recall our residual plot. This is what we did before. Okay, this was a residual situation before, and then this was a residual situation afterwards. We said that there was a clear pattern in the previous one, so we solved it by, who can remind us how we got back this residual on the right? What did we do to get back this residual on the right? Do you remember? What did we do to get the residuals on the right? What we did was we took the log transformation of the data. That's it. So after taking the log transformation of the data, you have this issue on the right. Now, how do you check whether there is autocorrelation? Several methods can be used. We've talked about the residuals, which is a visual inspection, but you can use, and you should use, statistical tests. Statistical plots are very powerful. They will be able to show you the real situation. Now, the statistical plots include the Watson test, and that's the one we shall use. That's the one most people also use. But there's also have the Jambox test and other ones. But the DW test is very key. You can also look at a visual plot. Let's look at a visual inspection. One of the things you can do is that you can plot the autocorrelation function. Graph of the correlation of the time series, you graph that together with the lags. And it will help you to detect the presence or the absence of autocorrelation in the residual. So first, you need to have the residuals. Okay? So you import this Watson package or library. From stats model, you now import the autocorrelation function, and then you plot the residual, okay, and set the p-value to 5. If you do that, and you do that correctly, this is what you're going to have here. And in fact, let me show you something. That's what you have here as well. Now look at the autocorrelation function, okay? And you will see that the vertical axis has a negative to positive value, and then 0 is in the middle. But look at the horizontal axis. You have 0 to 5 all the way up to 40. Those numbers from 0 to 5, they are the lags. They are the time. And we use AR1. So that means that we are looking at a lag of what? 1. And so you can see that the line here, the line is showing at 1. If you trace this vertical line down, it will meet you somewhere around 1. Okay. And you can see clearly, and that is what the lag we are looking at. If we look at other lags, we'll know how the whole thing is. When you look at this data very carefully, you can see the majority of the data just at the lag of 1. We're not going to other lags. Okay, at the lag of 1, okay, you can see that at lag 1, at the autocorrelation of lag 1, all the others are around 0. All of them. are around 0. And that is very important. But this is just a graph. Let's look at it mathematically by using the Debbie-Wasson test. Again, the null hypothesis is that rho is 0. Rho is 0 means that there is no first order autoregressive scheme. Okay, so AR1, there's no AR1. There's no autocorrelation. The alternative says that there is some autocorrelation. How do you check it? Normally, if you have AR1, you use a Debbie-Wasson test, and this is a test. It's a very beautiful test. If you look at it, the test is made up of several things related to the errors. Okay, so this one is looking at the difference between the error of today and the error of yesterday, the square of that, all divided by the square of the error of today. But then you take the sum of each one of them. So if you have the values of the error, you can easily calculate this. And we can prove that this Debbie-Wasson test is equal to 1 minus the estimated rho. The estimated rho. Okay, that rho that you had from here, from this error model, when you get a value and you substitute that value there, okay, and you subtract the value from 1 and multiply the answer by 2, that gives you the Debbie-Wasson. That's basically the point. So how do you now conclude? If the rho is 0, what do you think will happen here? If the rho is 0, what do you think will happen? If you replace this value, let me do it here. If you replace this value here with 0, then it means you're going to have 2 times 1, isn't it? Because 1 minus 0 will be 1. So 2 times 1 will be 2. And that means that the Debbie-Wasson here will be 2. And if the Debbie-Wasson is 2, it means that the errors are not correlated. Is that a correct one? I just said. Yeah. Okay, let's see. I think I may have made a type. If the rho is 1, okay, if the rho is 1, yes, right. If the rho is 1, you can see that 1 minus 1 is 0. So 0 times 2 is 0. So it means that the Debbie-Wasson will be 0 or will be moving towards 0. And that means that we have a positive autocorrelation. Now, there is a range of numbers they all call that will give you. And again, if the rho is -1, because remember, rho is between -1 and +1. If the rho is -1, then you have 1 minus 1, which means 2 into bracket 1 plus 1, which means 2 into bracket 2, which means 2 times 2, which means 4. Okay, so if rho is -1, Debbie-Wasson is 4, and that means that there's a negative autocorrelation. So what do you see about this whole thing? Okay, you can have 4 all the way there, you can have 4 all the way there, and you can have 2 in the middle. So what is usually the decision when it comes to Debbie-Wasson? Well, there are 2 critical values that will help you to be able to make your decision. Critical value number 1, let me clear this first. Critical value, okay, you need to compare the estimated Debbie-Wasson that you have against the upper value and the lower values of the critical values. I'll give you an example. And it's very important that you appreciate this thing. It's the same thing I'm showing you here, but look at it very carefully. Look at it. When you calculate your Debbie-Wasson, okay, and it is 2, if you can remember here, okay, if it is 2, it means that there is no autocorrelation. There's no autocorrelation. But then this has given you a range for you to know that is because it's not always going to be 2. So there's a range when it is a slightly below 2 and slightly above 2. It is still no autocorrelation. Take note. Okay, that's the most important thing I want you to take. So we have put a good map, which is 1.5 and 2.5. This value is telling you that there is no autocorrelation. So the null hypothesis that says there is no autocorrelation. Don't reject it. Take it. But at what point do you deviate? The moment you have the upper value. So anytime you have the value being further away from 2, way further away from 2, towards positive 4, as you can see, then we have autocorrelation, but it's autocorrelation of negative. When the value is moving towards 0, we have positive autocorrelation. And you can see this here. Okay? When the value is moving towards 0, there is positive autoco. When the value is moving towards 4, there is a negative autoco. So you just have to check that and use that to make your conclusion. So let's apply the Durbin-Watson on the OLS residual. It's very simple. All you have to do is to just say Durbin_Watson into bracket, whatever the residual is. And when you do that, you get this value. Who can tell me the conclusion here based on the value we have? Based on the value, Salasi.
Yeah, based on the value means there's no autocorrelation.
Exactly. There is no issue of autocorrelation in this model. That is how you basically do. So why did I not quickly jump and come and show you the Durbin-Watson results? It means you got to know what you are doing. You got to understand the residuals. You got to understand when the residuals are correlated across individuals and across time. And that is why we have to go through this. Another test you can use is the Jambox test. I'll not go into full details about it. Just note that it is a multiplicity of tests put together. It's a portmanteau test. It tells you whether any of the group of autocorrelations of the residual is different from 0 or it's not. Okay. But most people will use the first one. And then we have the Ricci-Godfrey LM test as well. But what if autocorrelation exists? The one we just saw, it doesn't exist. What if it is there? If it is there, then you got to try a different functional form, the log. Now, it's possible that the log that we took is why, in this case, it is not there. That's why, possibly. So you got to try a functional form. And that is what, this is very important, guys. This is very important. Transformation is very important. Okay. Sometimes you may have to delete some variables. Okay. And more importantly, if it is there, and so what? So use a newer West method. It's the best. It doesn't only solve the problem of autocorrelation, it also solves the problem of heteroscedasticity. And so this test, all it does is that it does not touch the coefficient. It only touches the standard error. And remember, the coefficient divided by the standard error will give you the t-states. It touches only the standard errors. It creates and gives you a new standard errors, which you can now divide the coefficient with, and then find new p-values and new anything that you want to. The good thing is that it is solving both heteroscedasticity and auto. So it's sometimes called HAC, H-A-C. That is heteroscedastic autocorrelated consistent standard error. That is a newer West standard error. It's the best. And if it is there, use that to run the model, and then you can speak that. Another final thing you can do is that you can increase the sample size. Okay. You see, something can be big when you have more solutions, or when you have more ways of dealing with the matter, then the issue becomes a non-issue. I'll give you an example. It's not the best of example though. Okay. A husband can be fooling or messing up, maybe insulting the wife, maybe doing certain things the wife doesn't like. Then one day he buys a car. or something, a house, and gives it to the lady. On that day, and then maybe subsequent times, you see that the lady will forget all the problems this man may have caused. Remember, I told you that it might not be the best example. Okay. That's the same, that's it. Okay. And so increase the sample size. Okay. And that may help you to deal with the time autocorrelation, okay, the time-dependent autocorrelation that you may have. So our final model, after solving these things, this is our final model. Our final model is this. The log of the sales is equal to 4.6 plus 1.95 item MRP plus item fat content regular plus blah, 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 plus 1.7 outlet type supermarket plus that, plus that. This is our final model. Okay. And when you want to interpret the first independent variable, the first independent variable is MRP. It means that a 1 unit change, I'm using change because of the log. Okay. A 1 unit change in the MRP, okay, then the sales or the outcome variable here, which is the sales, the log of the outlet sales will increase by 1.955 units. Now watch it. I said the log of the outlet sales will increase. I did not say that outlet sales will increase. No. If you want to say outlet sales, if you don't want to use the log of the outlet sales, because that's what we used. But if you don't want to use the log of outlet and you want to look at it, because a manager will tell you that, what do you mean by the log of outlet sales? I don't understand that. So in this case, you can interpret it in percentage terms. You can say that a 1%, increase in MRP will increase outlet sales by 1.9 blah 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 percent. That's how you do it. Okay. So if you want to increase sales, basically, you may want to store higher MRP items in a high visibility area for people to see it. And when the people see it, they will buy more. The key point I've shown you up here is this. Okay, is this final model, which is called the estimated regression equation. You can use this one to predict. You can use this to predict. You can say that, suppose you have a value of item MRP, and that value is 20. And then you have another value of item fat content regular, and that is 60. And then you have outlet type supermarket. And this is maybe a dummy of 1. In fact, the supermarket 3 is not here. 3 is here, so it means that the grocery store is not here. So the grocery store becomes the reference category. So if we know the value, if we know that an outlet type supermarket is not there, then it will have a value of 0. If outlet type supermarket type 2 is also not there, it will have a value of 0. If outlet type supermarket type 3 is there, then it will have a value of 1, making the grocery 1, 0. So it means that you will have the value here. I'll just show you. What it means is that we can predict. I'm just showing you prediction. You have a value here to be 1, a value here, because these are dummies, to be 0, a value here to be 0. Okay. And let's say that MRP is, say, 50, and then fat content is, say, 40. If we know these values, we can now substitute these values like I've done here, multiply and add, and then you can now use that to predict the log of sales. Okay. So having the final model is good because you can use it to do prediction. Finito. Now look here. Go through the others and then try and see if you can interpret them. Okay. How, if more, or what do you call it? If autocorrelation exists, I've given you an appendix here for you to check. If it exists, how you can check to solve the problem. I've already told you how to solve the problem. but this is an R Python command that you can use to solve the problem in case it exists. The heteroscedastic command that I told you is here. Okay. You can use that to check, and that will give you a robust OLS. Suppose they are clusters. You can use the cluster model. And I've given you a link where you can learn more about this autocorrelation and how to solve it. Good. Ladies and gentlemen, that is how you look at regression diagnostics. There are a few more diagnostics, but I've not looked at them. I don't want to look at them. You look at them in later times. But remember that you can't just do a regression and leave it. Check whether the assumptions of the classical linear regression model, the OLS regression model, check if the assumptions have been met. And once they have been met, you can proceed and do the rest. Next time, we will look at principal component analysis. The ladies are going to love this. Okay, that brings us to the end of the entire caboodle. Any question?